Thanks for coming out so early in the morning. I'm going to talk about swarm IoT. Swarms are in everyday life. Ants, birds, all sorts of swarming activity in nature. And we're going to talk a little bit about how to automate that and make it interesting for some of the missions that people have. What we're going to talk about today is the ability to put a single distributed controller program platformed on a large collection of independent IoT devices, either terrestrial-based devices or flying devices, and have no single point of failure. We are going to talk about high availability rollover, allowing for significant attrition but still completing the mission, and a swarm that's size and resource aware, so it can dynamically adjust up or down the strategies and tactics that it needs to accomplish. Let's talk a little bit about status. This idea, and this is a proposal, this isn't working, but it came out of our current products for our company, which is an application accelerator. We basically are able to implement a directed graph, if for all you nerds out there, that's like a Gantt chart or a PERT chart, and as the foundation, going back to the pyramids really, of all task scheduling. All computer algorithms can be basically defined in a directed graph. And it's an easy and efficient way to define parallelism. We implement our directed graph application appliance accelerator on multiple custom chips. Right now, we're running with 6 to implement a 1,000 processor compute fabric. And you can link those appliances together to expand the fabric dynamically. We've got a C++ SDK and an appliance in beta release. We're working and finishing up an Apache Spark and TensorFlow integration under development. Our current numbers for Apache Spark are running about 70x a current server, which makes it the fastest deployment, we think, of Apache Spark for machine intelligence and big data. Applicable to all algorithms, as I said, big data, AI, simulation, analytics, stream-based, and you can operate outside a data center. You don't need a data center to do this. What we're going to talk about today is swarm IoT is the high availability aspect coupled with self-awareness. The environments that these things are going to be deployed in are going to be very harsh. Node failure expected. Failover must be distributed. And you need to resize your strategic goals and tactics as the swarm grows or shrinks. And there are a couple ways to do that. You can suggest hierarchical function organization, either from the military aspect, division, brigade, battalion, on down, or you can look at a biology approach, body, organ, subsystem, cell, similar approaches to take. Now, the key secret sauce here for the company and for this idea is that we have developed a way, rather unique in computer science really, to be able to take and expand a large collection of processors, and in all other cases other than ours, when you did that, the overhead for all the processors to coordinate and communicate with one another increased exponentially as you added more processors to your problem. We've developed a way where that does not happen, that the overhead doesn't increase exponentially, but stays at a constant percentage of the available processor fabric. And what that means is we can dynamically create and execute directed graphs of infinite size, which means that we could deploy a 100,000, 200,000 swarm of objects that are all basically representing a single directed graph. They all support the platform of a single graph. And that means a platform of a single intelligent entity. And that's actually both terrifying and exciting at the same time. There are lots of interesting science fiction-y things that have been written about over the last 20 years. The Borg, for one, from Star Trek. Prey from Michael Crichton, for another. And you can probably all think of use cases both wonderful, like environmental disaster remuneration, or or warfighting types of scenarios. Okay, so what we're talking about is each device has its own processor fabric chip. You can stitch the devices together with a radio link to form a single fabric and a single directed graph and algorithm running on that. And each device basically needs a secure radio link to a small number of neighbor devices, and you're going to assume unreliable links are going to be going up and down at the, basically with great frequency. But overall, you get the same effect of an intelligent swarm to be able to perform whatever missions you want to define. And I'll take some questions. I've blown people. Okay, go ahead.
So what's the largest deployment you've done to date?
Well, we're doing 1,000 processors today on 6 chips. And that's basically, we're going after the appliance market for data centers today, but we're talking to people to take advantage of these large processor fabrics for lots and lots of use cases, for machine intelligence, for Apache Spark and TensorFlow, obviously, but for other areas like bringing processing closer to the edge. I have one group that I'm talking to that wants to bring processing for radar images out from the ground station and into the sensor itself. Another group that wants to do simulations for very, very large capital equipment instances so they can do preemptive maintenance. Another group that's interested in taking a very large core fabric and doing molecular three-dimensional configuration so they can do the physics on each atom in a very large biomolecule and do protein engineering. So lots and lots of interesting use cases. We think this will fundamentally change the direction of enterprise computation in the future, as it allows for massive parallelism to take advantage of all the parallelism available in a directed graph representation of an algorithm.
Just one more. Can you speak to the resiliency of the systems? I know you and I had talked about that briefly, and I thought that was an interesting point because
So the resiliency of the system is important because what we're going to have is a growing or shrinking large-scale directed graph that's self-aware. So if you think about it, you have basically an intelligent entity platformed on all these devices that can afford to lose if it, 50, 60, 70%, and still basically achieve the mission. Or if it finds cut-off devices, it can reabsorb them and get stronger. So this really is a very adaptable type of concept for a very harsh environment. I mean, one of the things that I found interesting was last year I was at Fort Fisher, which was where the last major battle, one of the last major battles of the Civil War was fought. And they had a beautiful lit table of how the battle unfolded. And they saw how the various forces went ahead and achieved their objectives when they attacked the fort. And you could think about using these kinds of technology in the same way, that they are forces that are executing a particular tactic appropriate to their size and capabilities to achieve defined objectives. And if those objectives, if the forces get reduced, you can reduce down the strategic goals and still achieve great objectives just in the same way that a typical military unit would be able to do. Other questions? Nobody else? So a practical example, I'll give you a safe one, oil spill. So right now, you deploy lots of people on lots of booms. You could deploy land-based or water-based devices that would basically, in large scale, that would be able to sort of do a small task, but you'd have a lot of them being able to work in that environment. You could use this technology for swarming UAVs. So that if you wanted to take a military objective with a large number of UAVs, say 10,000, 100,000, there would be no single point of failure for the enemy to take out the entire offensive. That if the enemy was able to take out a significant portion of them, you would still be able to achieve maybe more limited goals, but still achieve some military objective. So it's a very dynamic thought process to think about the same way you would use manned forces and how they could basically define, you could give them orders on, You know, if you get cut off, these are the types of objectives you could do. If you form up with larger groups, you can achieve greater strategic objectives. Same type of approach, but automated.
So your software lives on a chip on each piece, on each one of those entities, and then communicates with the other thing.
Right. There is one singular intelligence platformed on top of all the underlying entities. That's the hard part to get your head around.